I don't normally like getting up in the morning, but old Mr. Sun is shining down on me. So you chipped your nail, you stubbed your toe, you lost your phone. Life's a rolling stone on a broken roller coaster. Scream shit, move on. Throw your hands up, move on. It's all good.
Today we're going to talk about superposition. Now you're probably familiar with superposition in other areas. The principle of superposition effectively says that a whole is the sum of its parts. So you can take individual parts, individual components of a system, add them together to figure out, some bigger quantity. An area where you're probably familiar with this most is in the area of like vector addition. So let's say that we have a vector here, that's vector 1. Okay, vector 1's going off in that direction. But you know if you place this on a coordinate system that you could break down a vector going in that direction and a vector going in that direction. You could say this is v1 in the x direction. This is v1 in the y direction. And those are individual vectors themselves. But you can take these individual vectors, add them together to figure out what the resultant vector is. That is really superposition. The sum of the individual components is equal to the vector. Now, the sum has to be done correctly. You don't just algebraically add these together for vectors. You have to add them like vectors, and there are certain rules for that, and you've seen that. Well, when it comes to circuits, the principle of superposition also applies. It applies specifically to linear circuits. And by the way, almost entirely all of the circuits that we will encounter in our class are linear in nature, which just means the output is linear related to the input somehow. Okay? So if you have a linear circuit and it has more than one independent source, then the total response is the sum of each of the responses individually. Let me kind of show you what I mean by that. Let's say that we've got this circuit here. This circuit has two independent sources in it, you see there. If I wanted to know something, let's say I want to know the voltage, the output across the 10 ohm resistor there. Well, I could obviously solve this circuit using some of the techniques that we learned in here. But the principle of superposition says that if I disable this source, the 110 volt source, so let's say we disable that one, then I can figure out what the voltage is due to this 4 amp source, only the 4 amp source. And I can determine what that voltage is. Take that value, set it aside, then come along and do the opposite, disable the 4 amp source and keep the 110 volt source. Then figure out what V0 is one more time with just the 110 volt source. Then take those two voltages, one for the 4 amp source, one for the 110 volt source, add them together, and for circuits you just algebraically add these together, but you add them together and the resultant is V0, which is the output voltage across the 10 ohm when both sources are present. So you essentially solve the circuit twice and then sum up the results. Now, that's the principle of superposition. So the voltage across or the current through an element in a linear circuit like this is just the algebraic sum of the voltage across or the current through that element due to each independent source acting alone. All right, so if we wanted to solve this circuit using superposition, we would actually have to solve it twice. That's a major disadvantage of this technique. It adds a little more work, but it also simplifies things because you only have one independent source at a time. Now, also another thing concerning this is that it really only allows you to disable the independent sources. So in this one, it wouldn't be a problem. But if there is a dependent source in the circuit, you cannot disable the dependent source at any time. So you've got to leave those dependent sources there regardless whenever you're solving. All right, so let's see how to do this using a simpler circuit. Let's say we've got this circuit. All right, for this circuit we have two independent sources, and what we're after is the voltage across the 4 ohm here. Now, superposition is the technique we're going to use here, and superposition will work as long as we're trying to find a voltage or a current. That's because those are linear relationships, voltage and current. You know that V equals IR. That's a linear relationship. So V and I are directly proportional to each other. It's a pretty simple linear relationship here. So it applies to voltages or current. It does not apply to powers. So if I wanted to compute a power in here, I could not do that directly. Why is that? Well, P equals I squared R. This is not a linear relationship. It's also V squared over R, not a linear relationship. But it's also equal to I times V, and when you multiply those two together, that's not linear either. So it applies to determining voltages and current. It does not apply to determining powers directly. But you can determine the voltages and currents individually and then figure out what the power is. So it is possible to do it that way. But let's take this circuit right here, and we're after the voltage, so everything's linear here. And let's use superposition. So here's what we want to know. We want to know the voltage across the 4 ohm, so let's let that voltage equal what we'll call voltage 1 and voltage 2. Now, voltage 1 and voltage 2 are the two voltages when the two sources are present. So we'll let voltage 1 equal the voltage. So voltage 1 is the voltage due to the 6-volt source. So we'll leave the 6-volt source in there, disable the 3 amp source, and that'll be V1. And then V2 is, voltage 2 is the voltage due to the 3 amp source. So for that one, we'll disable the 6-volt source, leave the 3 amp, and figure out what it is there. And then in the end, after we figured out what V1 and V2 are, we'll just add those together to figure out what V is. And then we're done at that point. Okay, so let's do the steps here. Let's figure out what V1 is first. So we're going after V1. All right, we need to turn off the 3 amp source and find V1 at that point. Now, when you turn off a source, it is different the way you turn off a current source as opposed to a voltage source. You do not disable them in exactly the same way. To disable a current source, you literally remove it from the circuit. So you leave a hole there where it was. So when you disable the 3 amp source, the circuit becomes this. And now V is V1. Okay, so we just left a hole there. I didn't draw the wires over here, but that's where it would be. Those wires are serving no purpose now, so we could do away with those. But we've disabled the 3 amp source by literally removing it from the circuit. And what we have left here then is a voltage divider. So you can write down the equation for that just by inspection. It's going to be 4/12 of 6 volts. And what is that? 12 is 24, 2 volts. There. We figured out what V1 is. Now we're ready to figure out what V2 is. I'll flip over the backside for this. When we go for V2, what we're doing is we're disabling the 6-volt source and we're keeping the 3 amp source. So to disable a voltage source, you remove it and replace it with a piece of wire. So you remove it and replace it with a piece of wire. So the circuit in that case becomes this. All right, now you might recognize this as a current divider. So if we define the current I2 going through the 4 ohm here, then I2 is going to be 8/12 of 3 amps. 2 amps. And now that we've got the current by current divider equation, then V2 is just I2 times 4 ohms. So that's 8 volts. there. All right, so once again, we disabled the 3 amp source by taking it out and solve for V1. Then we disabled the 6 volt source by replacing it with a piece of wire and solve for V2. The last step is to figure out what the voltage is. It's simply V1 plus V2. V1 was 2 volts plus V2, 8 volts. Answer, 10 volts. So the voltage across the 4 ohm resistor is 10 volts then. And we've got our answer at that point. All right, now that you kind of see the process here, let's go to our more complicated circuit here. What we want to do is we want to find V0 using superposition. So let's let V0 equal V1 plus V2, where V1 is the voltage due to the 110 volt source, and V2 is the voltage due to the 4 amp source. All right, let's go for V1 first. So we're trying to solve for V1. We're going to disable the current source up here. We're going to keep the 110 volt source. So the circuit looks like this then. We disabled the 4 amp source. We removed it from the circuit. And the voltage that we're after is now V1 across the 10 ohm. We don't use the same notation because this will be a different voltage than V0. All right, now you use the techniques that you know about to solve this. I believe that we could take this and turn it into a voltage divider by combining the 12 and the 2 to make a 14, and then that combination is in parallel with the 10. So the voltage V1 is not going to change in that case. So this is a 10 in parallel with the 14. Let's see what that turns out to be. So that's what it turns out to be right there. Now that we've got that, V1 is pretty straightforward. V1 is 5.833 divided by 10.833 of 110 volts. And when we do that computation, 59.23 volts. Okay, so there's our V1 value. Now let's do V2. And for V2, we're going to disable the 110 volt source, so we're going to replace it with a piece of wire. And now the voltage we're after is V2. All right, what we need is we need the current through the 10 ohm in order for us to get the V2. There's several ways we could do this. We could use KVL, KCL. There's even looks like a T here. We could use Y delta. Maybe that would help. We could use series parallel reduction after that. Series parallel reduction will work here too right away. I don't know if you noticed, but this 10 ohm and the 5 ohm, those are in parallel with each other. You see both ends of both resistors are connected together. This one is connected and they are connected here as well. So those two are in parallel with each other. So it may be easier to take these two, combine them together, figure out what the current is, and then go from there. That should be helpful. Let's do that. This one here, since these two elements are in parallel with each other, the voltage will be V2 over both of those. So this is the 10 in parallel with the 5. And let's see, what would that be? 50 divided by 15. 3.33 ohms, and there's a current going through this. We'll call that I2. But there's a current going this way. Let's call that I1, since we called that one I2. The current going through that is going to generate voltage too. So in order for us to figure out the voltage across this, which is V2, I don't have room to write that in there. But V2 can be computed once we know what I2 is, because we'll just multiply I2 times 3.33, and then we've got it. All right, well, I2 is going to be pretty straightforward, because now you see this is a current divider. So we've got a current coming in and dividing into I1 and I2 here. So we can write the I2 equation from divider equations. So that's going to be 12 over 12 plus 5.33 of 4 amps. And that turns out to be 2.77 amps. So there we have I2. Now, in order to get V2, do we write V equals IR or V equals minus IR? V2 is going to be equal to, all right, well, notice the voltage here is plus minus that way. So it's going to be plus minus that way. The voltage, I'm sorry, let me say that again. The current I2 is entering the negative terminal here. So when we write the voltage equation, we need to write minus I2 times 3.33 ohms. So that's going to be minus 2.77 amps times 3.33 ohms. That's going to be minus 9.23 volts. There is V2. So here's V1, here's V2. Now, in this tiny little space down here, we can come up with this final answer. V output is going to be 59.23 minus 9.23. Looks like 50 volts is what the answer is for V0. Now, at this stage, if you needed to know what the power dissipated by the 10 ohm was, you could use this 50 volts and do P equals V squared over R. So the power for the 10 ohm would be 50 volts squared over 10. And let's see what that is. 250 watts. Now, we weren't asked for that, but the point here is you cannot compute power 1, power 2, and add the powers together, but you can do that with the voltages, and then as a last step, you can figure out what the power is based upon that voltage. Now, here's the important thing, and I said this before. When applying this principle of superposition, it really only works if you have independent sources. If you have dependent sources, it still works, but you cannot disable the dependent sources. You can never deactivate the dependent sources. So let's do an example with a dependent source so you can see that. All right, so here we've got two dependent sources and two independent sources. Notice I delta is defined here, and this dependent source is controlled by I delta, so this is a current controlled voltage source. So 2I delta is going to be the voltage here. And then we have a voltage controlled current source that's controlled by V delta, and you can see V delta is defined right here. But what we're after is V0. We need to find V0 using the principle of superposition. We can disable one at a time the two independent sources, but we have to leave the dependent sources there. All right, so let's begin. We're going to let V output equal V1 plus V2, and let's define V1 as the 10 volt source only, and V2 is going to be the 5 amp source only. All right, so we are going to first disable the 5 amp source, and when we do that, we just remove it from the circuit, leave an open circuit there, so these wires will disappear. And for V1, the circuit looks like this. Notice I call this V delta 1. It's no longer V delta. Now it's V delta that goes with voltage 1. So that's the reason for the change in notation. We'll do that with other elements too here. So here we have V1 now. That's what we want to solve for. And we've changed our notation. I've left off I delta. So this is now I delta 1. Well, in order for us to find V1, we're probably going to have to deal with these delta variables out here as well. So let's spend some time talking about those. It may be that you don't always see what you're supposed to do, and maybe you just need to play around with the circuit a little while to figure things out. I do notice that if I use Ohm's law here, then V delta 1 is equal to minus I for 10 ohms. So if I imagine the current, and this section here, this branch, is going to have all the same current. What is that current going to be? It's going to be 0.4 V delta 1. So that's the current through this branch. And I notice that current enters the negative terminal of the 10 ohm resistor. So I can write Ohm's law this way for the 10 ohm resistor. V delta 1, that voltage there, is equal to minus I times the resistance of the 10 ohm. Now I can substitute in for I. That's going to be minus 0.4 V delta 1 times 10 ohms. So V delta 1 is equal to minus 4 V delta 1. Okay. I can see already what's going to happen here. When is this going to ever be a true statement? That V delta 1 is equal to minus 4 V delta 1. There's only one solution for that, and V delta 1 has to equal 0. So at this point, that dramatically reduces down what's happening here. Okay, we can just ignore this part of the circuit then, and the circuit becomes that. So in that case, V1 is equal to 20 over 25 of 10 volts. And that turns out to be 8 volts. There, we just figured out what V1 is. All right, that turned out to be very simple, because what's happening over here on the right-hand side of the circuit doesn't matter. There's no voltage across the 10 ohm. If there's no voltage drop across the 10 ohm, why is that? Well, that means there's no current. Because you know V equals IR right here. In order for V delta 1 to be 0, I has to be 0. So there's no current flowing over here. This is just a dead part of the circuit then, and we can ignore it. And that's why it became very simple at that point. All right, we still have to get V2. For V2, we replace the 10 volt source with a piece of wire and allow the 5 amp source to stay where it's at. And in that case, the circuit looks like this. Okay, so here we've got our 5 amp source. We've disabled the 10 volt source over here. Notice we've also changed our notation. V delta 2 and I delta 2 are now defined, and we need to determine V2 here. All right, well, one of the things that I see right off the bat is that we can combine these two resistors together, and it's not going to change our voltage V2. So let's do that. And now this is the 5 in parallel with the 20, so that is 100 over 25, so that is 4 ohms. We know the current through this. The current through this is going to be 0.4 V delta 2. If I can get the current through that then I can write the equation that V2 is I times 4 ohms. and that I is 0.4 V delta 2, so really I need V delta 2 in order to get the current so that I can get V2 now. All right, well, V delta 2 is equal to its current times 10 ohms. That's just Ohm's law applied here. Now we don't know the direction of the current through that, but we can assume a direction. And when we assume a direction, if it goes into the positive terminal, then we can write it this way. Let's just call that I there. That I is not this I though. So this I is 0.4 V delta 2. That's what goes there. That I is this I. And if we look at this top node here, we have a current of 5 amps going in that is being split there. So just writing a KCL equation for that top node, 5 amps is equal to I plus 0.4 V delta 2. Okay, from that, we see that I is equal to 5 minus 0.4 V delta 2. What we can do, though, is we can take this I, substitute it in here, and then we just have one equation with one unknown. So let's do that. Let's take that, substitute it in right here. Then V delta 2 is equal to I, which is 5 minus 0.4 V delta 2 times 10 ohms. All right, let's multiply through. That's going to be 50 minus 4 V delta 2. So V delta 2 is equal to 50 minus 4 V delta 2. Let's take that minus 4, put it on the other side of the equal sign. Then we have 5 V delta 2 is equal to 50, which makes V delta 2 equal 10 volts. Okay, that's V delta 2. Now let's take that back up here so that we can figure out what our V2 is. V2 is going to be 0.4 V delta 2, 10 volts times 4 ohms. So that's going to be 4 times 4, that's going to be 16 volts total. Okay, now a word about the signs here. You notice, the units here. You notice that what's in parentheses there should have a unit of current, and I've written down 0.4 times 10 volts. Well, when you do the multiplication here, that 0.4 actually has a unit associated with it, so that when we multiply by the voltage of V delta 2, it turns out to be I. So all of that right there, I know it's engineering, it's not physics. It has a unit of amps. An amp times an ohm is a volt. So V2 is 16 volts. All right, now we have V2 here. We have V1 back here. So there's V2, there's V1. So V naught, V output, V naught, is equal to 8 plus 16 volts, which is 24 volts. There's our final answer for what V naught is. This is the one that counts right here. All right, so answer V naught, 24 volts. There. And we did it by not disabling the dependent sources at all. All right, so we've got two independent sources once again, but we also have this dependent source which we cannot in any way disable. And what we're after is V naught over here. So let V naught equal V1 plus V2. And let's let V1 equal, let's say, the 15 volt only. And V2 equal the 8 amp only. Now you can do the two circuits where those are turned off or disabled, and you'll get two different circuits there. Each one of those should have one independent source and the dependent source at the same time. Let me tell you what the answer is, and you need to do this one on your own. First of all, V1 is 7.4 volts. V2 is 24.6 volts. That means V output is going to be 32 volts. So that's the final answer for V output. I would recommend that you do something like use PSpice on this one. Use PSpice to see if you can determine that V1 is indeed 7.4 volts when you disable the current source and have only the voltage source there, and that V2 is indeed 24.6 volts when you disable the voltage source and keep the current source there. And if that's true, then the grand total of those two is going to be 32, and there's your answer. So I would recommend that you do that. Use this as a practice problem. You can either do it by hand, but I'd recommend you do it by PSpice, because in your future sometime you're going to have to use PSpice. All right, so with that, we are finished with superposition, and we will move on to something cool and better next time.
You chipped your nail, you stubbed your toe, you lost your phone. Life's a rolling stone on a broken roller coaster. Scream shit, move on. Throw your hands up, move on. It's all good. Today is your day. Time is filled with swift transition. Put yourself in good position if you want. Things can go your way. Ain't no time to smell the roses. Gotta get to where to go. The road's already been paved. Here I go. Ready now, I'm coming for you. Can't nothing stop me. I got some things I gotta do. Hey, 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 hey. I'm making a move. Study long, study wrong. Ain't nothing gonna happen on its own. I'm making a move. Don't need no hickeys for this song. I got joy all through my soul. I'm making a move. Get up, get out. Mr. Sun is shining on me. I'm making a move. Big days on the horizon for anyone willing to play. You gotta move, you can't lose. Get in the groove, you can't lose. Speed bumps only make you aware. It starts in your heart, so reach for the stars. You know you got charm, you can't do no harm. I hope you're prepared, cause when you get there, you'll be laughing and wilding like the principal there. Here I go, ready now. I'm coming for you, can't nothing stop me. I got some things I gotta do. Hey, 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 hey. I'm making a move. Study long, study wrong. Ain't nothing gonna happen on its own. I'm making a move. Don't need no hickeys for this song. I got joy all through my soul. I'm making a move. Get up, get out. Mr. Sun is shining on me. I'm making a move. Got my lucky charms and to move along. Yeah. On its own, I'm making a move. Don't need no hickeys for this song. I got joy all through my soul. I'm making a move. Get up, get out. Mr. Sun is shining on me. I'm making a move. Got my lucky charms and to move along. Yeah, I'm making a move. Might as well choose the daily. I'm making a move.